Chapter 4 notes light and atoms. All right, so light is the astronomer's tool. Remember that it's not like we can go and take a sample off of Pluto. We can't go there and take a scoop of it or pick up rocks off of it and bring them back to Earth and study it. We can't do this with stars. We can do this with none of these astronomical bodies that are far away from us. So we use their light to find out what they're made of, what minerals, what elements make up that planet or that star. And we use this by doing experiments with light. Understanding the properties of light is essential because of this, all right? And we have to be careful because with our atmosphere, and it's talking about the atmosphere down here, with the atmosphere, we tend to filter out. Some of the light is filtered out in our atmosphere, the ultraviolet light. Some of the infrared light is filtered through our atmosphere. So this makes it sometimes a difficult task. Remember, light is radiant energy. It's an electromagnetic wave or a photon. And it does not require electromagnetic waves do not require a medium, unlike sound. Sound waves need a medium. Light travels at a very high rate of speed. In a vacuum, this was discovered in Cleveland at Case Western Reserve, and we give it a small c, is what the speed of light stands for, small c. That didn't sound right. Small c stands for the speed of light. And even though it seems high, like a very high rate of speed, when we're talking about astronomical bodies other than our own solar system, it's not as fast as we would like it to be. It'd be easier if it was a little quicker than that. But anyway, remember also that as light, the speed of light, when an electromagnetic wave passes through a material, it changes speeds. Sometimes light can be modeled as a wave, and here's the wave. We also watched that short video on it, okay? Here's electromagnetic energy, the electric energy in the red, and the magnetic energy in the blue. And this alternating pattern causes it to travel through the air. The wave travels as a result of a fundamental relationship between electricity and magnetism. A changing magnetic field creates an electric field, and a changing electric field creates a magnetic field. Sometimes it can be modeled as a particle instead of it being an electromagnetic wave. It's a particle. That particle is known as a photon. Light thought of as a stream of particles is called photons, and each photon particle carries energy depending on its frequency or its wavelength. So, which one of these models do we use? It depends. In a vacuum, photons travel in straight lines, but behave like waves. Subatomic particles also act like waves. Your subatomic particles, electrons, protons, okay? Wave particle duality. All particles of nature have both a wave and a particle property. The model we use to describe light's behavior depends on the situation. We can concentrate on the wave picture henceforth. So in this class, we're going to use mostly the wave, okay? We'll talk about photons a little bit, but waves are much more easy. The electromagnetic wave is easier to understand. So that is the model that we will use. All right, so the colors to which the human eye is sensitive is referred to as the visible spectrum. In wave theory, color is determined by the wavelength. And here's our wavelength, crest to crest, trough to trough, all right? Or you could go rest to rest. It doesn't matter. But this is our wavelength. And color, the different colors, Not sure what happened there, but the different colors are determined by the wavelength. Okay, the wavelength. The wavelength is signified by the Greek letter lambda. Nanometer is the convenient unit when we're talking about the visible spectrum. Reds are 700 nanometers. Those are the longest visible wavelengths. And violet are the shortest visible wavelengths. So here we see the visible spectrum. Now, this is the spectrum as far as we know right here. And we only see this tiny little bit between 400 nanometers and about 750 nanometers. As you get older, as a person ages, this becomes smaller for you. You don't see the bright reds and the lower purples. But anyway, you can see how this works. The longer wavelengths are over here, radio waves, AM. And then we go down to gamma rays, which are the smallest electromagnetic waves. And again, in between, in this little area, this is what human beings see as light. All right, sometimes it's more convenient to talk about the light's frequency. Frequency, or V, is the number of wave crests that pass a given point in a second, measured in hertz. All right, so frequency is a form of velocity. How fast is that wave going? How many waves pass per second? So the relationship here is frequency, or how many waves pass per second, times the wavelength, and that will always equal the speed of light. Long wavelengths have a low frequency, and short wavelengths have a high frequency. So white light is a mixture of all the colors, and we know this because we take that light from the sun and we slow it down through a medium. When it's slowed down, it breaks into the different wavelengths of light, all right? And we can see the complete and total spectrum. A prism demonstrates, while white light is a mixture of wavelengths by its creation of a spectrum. A prism demonstrates that white light is a mixture of wavelengths by its creation of a spectrum. We can also recombine those to back into white light. Additionally, one can recombine a spectrum of colors and obtain white light. The electromagnetic spectrum is composed of radio waves, microwaves, infrared waves, visible light, ultraviolet, X-rays, and then gamma rays. The longest wavelengths are more than 10 to the third kilometer. That means from crest to crest, it's 10 to the third kilometers from crest to crest, where the shortest wavelengths are 10 to a negative 18 meters between crest to crest. Various instruments used to explore various regions of the spectrum. Infrared radiation. All right, so what happened here? Let me go back. So Herschel was actually measuring the temperature of the different light waves. All right, he had a thermometer and he used a prism, broke the colors into this visible spectrum. Now, at this point, before Herschel, we thought the only thing was this, that we didn't realize there were other wavelengths that we couldn't see. All we knew of was visible light. So Herschel actually, by accident, went over here and laid his thermometer out of the light and then went to grab some lunch. When he came back to take the thermometer and put it in one of these wavelengths, he noticed there was a different temperature on it. And that's how we discovered infrared waves. Okay, so let's right here. Sir William Herschel around 1800 showed heat radiation related to visible light. He measured an elevated temperature just off the red end of the solar spectrum, or the visible spectrum. And he called it infrared energy. And our skin feels this as heat. That infrared energy we feel as heat. Ritter in 1801 noticed silver chloride blackened when exposed to light just beyond the violet end of the spectrum, mostly absorbed by the atmosphere. So ultraviolet light is absorbed by the atmosphere. And what Ritter did He happened to put some silver chloride. He was looking at the spectrum and he put some silver chloride down in this place and he noticed that it absorbed some energy. And that was how we discovered the ultraviolet light. Ultraviolet light. Geez, oh Pete, ultraviolet light is responsible for suntans and burns. It is absorbed by the ozone layer. Radio waves. Radio waves were predicted by Maxwell in the mid 1800s, and Hertz produced the first radio waves in 1888. Another scientist, Jansky, discovered radio waves from cosmic sources in the 1930s, and this was the birth of radio astronomy. And we now use all kinds of radio telescopes. Next chapter is telescopes, and we're going to talk about these different kinds of telescopes. But we use radio waves all the time to study different astronomical processes. We can even hear the sounds from the other planets through radio waves. We use these radio waves for communication. Obviously, the radio, cell phones, and that are running on close to microwaves now. But microwave ovens use radio waves. And again, search for extraterrestrials. And when we're saying extraterrestrial, doesn't necessarily mean we're talking about little green men or anything like that. But we are searching for intelligence in the world other than ours. On the other end of the spectrum, we're talking about X-rays now. Roentgen discovered X-rays in 1859, and it was first detected beyond the Earth in the sun in the late 1940s. It's used by doctors to scan bones and organs, and it's also used by astronomers to detect black holes and gas in distant galaxies. We have telescopes out there made especially for picking up wavelengths in the X-ray category. Gamma rays. At this point, we don't know a lot about the gamma ray area out in the universe, and it's just simply because the Earth's atmosphere absorbs gamma rays. So we can't study gamma ray from Earth. We have to be out in orbit, whether you're on the space station or it's done with a telescope that's out there. So gamma ray region of the spectrum is still relatively unexplored. Atmosphere absorbs this region, so all observations must be done from orbit or from space. We sometimes see bursts of gamma ray radiation from deep space. All right, so energy carried by electromagnetic radiation. Each photon of wavelength, remember lambda, carries energy given by energy equals h, which is Planck's constant, speed of light times speed of light divided by the wavelength. Max Planck was the greatest astrophysicist of his time before Einstein came along. When Einstein wrote his papers, Planck was actually the only one that understood him at the time. So anyway, notice that a photon of short wavelength radiation carries more energy than a long wavelength photon. Short wavelengths, high frequency, equal high energy. Long wavelengths have a low frequency and they have a lower energy. Now, if we look at space through different types of telescopes, here's the visible spectrum. If we just look through a telescope and look at this area, we see this. You'll see a lot of stars and that. If you look at it in infrared, this is the same area, but in an infrared telescope, this is what we see. If we look at it through a radio telescope, this is what we see. Over here, if we look in an ultraviolet range, we'll see this. And in an X-ray range, we see this. All of these pictures are of the same area, just with different types of telescopes. Matter and heat. The ancient Greeks introduced the idea of the atom. If you remember, it's a guy by the name of Democritus. The ancient Greeks introduced the idea of an atom, which means uncuttable. Today, we know that an atom is broken down into several other parts, the nucleus and electrons. Also, heat, the transfer of heat and energy was a really important topic in the 17 and 1800s. That's because everything in the 1700s and the 1800s was driven by steam. Steam locomotives, machines in factories, all was driven by steam. And one of the guys that really worked with steam and that temperature energy was Kelvin, Lord Kelvin. An object's temperature is directly related to its energy content and the speed of the molecular motion. Also, a body is cooled to 0 Kelvin. Molecular motion, when within it, slows to a virtual halt, and its energy approaches 0. No negative temperatures. There's no negative temperatures at 0 degrees. Basically, at 0 degrees Kelvin, the electrons cease to orbit the nucleus. Fahrenheit and Celsius are two other temperature scales that are easily converted into Kelvin. So we go by the Kelvin temperature scale. And here's a little peek at the Kelvin scale. The sun's core, 15 million Kelvin. And here it is in Fahrenheit and Celsius. Surface, sun surface, light bulbs, water boils, the human body, 98.6. And you can see the Kelvin scale, Celsius scale, and the Fahrenheit scale all together. Wien's law. And it uses the Kelvin scale. Heated bodies generally radiate across entire electromagnetic spectrum. And before I go on to the next one, what we use Wien's law for is we can determine from an astronomical body's color and wavelength the temperature. That's what this is all about. Okay, so there's one particular wavelength, lambda m, at which the radiation is most intense and is given by Wien's law, where K is some constant and T is the temperature of the body. So again, we can find out the temperature of astronomical bodies through Wien's law. Note radiation and temperature. Note hotter bodies radiate more strongly at shorter wavelengths. As an object heats, it appears to change color from red to white to blue. Measuring the wavelength gives a body's temperature. You have to be careful though, because reflected light does not give temperature. You have to get that direct light. So you cannot get the temperature of an object if it's reflected. The hot burner glows more yellow than a cool burner. All right, so black bodies, ideal black bodies. A black body is an object that absorbs all radiation falling on it, all visible, the whole spectrum, visible. It absorbs X-rays, it absorbs ultraviolet rays, infrared rays, radio. It absorbs all of these, okay? And since an object does not reflect any light, it appears black when it's cold. So these guys back in the 17 and 1800s would take pieces of black iron and heat them at a blacksmith shop. And they would watch it change colors. And in all reality, as you light or heat a light, as you heat a black body, it goes through all these steps of the spectrum. And they would measure its temperature, okay? It would measure the temperature. As it would start to change colors, they would measure the temperature. All right. So get back here to black bodies. Boom, boom. Since as a black body is heated, it radiates more efficiently than any other object. Black bodies are excellent absorbers and emitters of radiation, and they follow Wien's law. Very few real objects are perfect black bodies, but many objects, such as the sun and the earth, are close approximations. So when we see other planets, when we see other stars, we can kind of get their temperature. All right. Gases, though, unless they are really highly compressed, are not black bodies and can only radiate in narrow wavelength ranges. So, if we're looking at different stars, blue tinged stars, a star similar to our sun, and a red star, we notice by Wien's law. I always say Wien, but it's Vine's. Anyway, our sun, this is more like our sun, you can see it radiates best in the visible light spectrum. That's what we can see. Where a red or an infrared light or star radiates brighter in this area, and ultraviolet or blue stars are going to radiate outside the visible spectrum. So it's hard for us to see anything that doesn't look like our sun without special instruments, without these special telescopes. Chemical elements. An element is a substance composed of only one type of atom that have the same number of protons in their nucleus. A neutral element will contain a number of protons and electrons. Oh, yeah, neutral. I'm just sitting here reading these off. Neutral elements have the same number of protons and electrons, and they cancel each other out. The charges cancel each other out. The chemical properties of an element are determined by the electrons. Remember, elements or atoms are determined by the number of protons they have. All carbon have 6, whereas electrons can vary, and electrons give us those chemical properties. We know that the structure of an atom, protons and neutrons, are in the nucleus. There is an orbital cloud around it of electrons, and atoms are pretty small, 10 to the negative 10 meters. Electron orbitals are quantized or quantized. I'll get it. Blah, blah, blah. Some of these words are rough on me. Quantized, which means you can't get more than a certain number of electron in each orbit. We already know this. All right. Quantized orbitals are the result of a wave particle duality. And as electrons move from one orbit to another, or one energy level to another, they gain or lose energy in a discrete amount. Okay. There cannot be orbital 2.5 or 2.35. They are always whole numbers. We talked about this earlier. An atom's energy is increased if an electron moves into the outer orbit. The atom is said to be excited. So as this electron moves, it gets excited, it expands, it's getting energy. Okay. And as an atom's energy is decreased, the electron moves to a lower orbit and gives off light or a photon. Conservation of energy. The energy change of an atom must be compensated elsewhere, or conservation of energy. Absorption and emissions. That's the waves it absorbs to get it excited, and it emits when it leaves that excited or when it condenses. Of radiation are 2 ways, or electromagnetic radiation are 2 ways to preserve energy conservation. In the photon picture, a photon is absorbed as an electron moves to a higher orbit, and a photon is emitted as the electron moves to a lower orbit. And again, as energy comes in or a photon comes in and hits the electron, we know this. If you've started your lab like you should know this. This photon comes in, hits the electron, energizes it, it goes up or out in orbit, and then when it falls back down or cools off and falls back down, it's going to give off an electromagnetic wave or a photon. Absorption. Absorption. A lot of these photons or waves coming in do not hit. It's got to be the right type of wave. Why this is important is each element absorbs different wavelengths, and each element emits different wavelengths. None of them are equal. So right here, we see that it takes a certain wavelength to excite the electron in a hydrogen atom. All right, these photons, these waves right here are not exciting this electron. And you, again, we saw this in the lecture I gave at the beginning of the chapter, and also you should be seeing this in your lab. So what this is telling us, this absorption and this emittance, is telling us each individual element has a different spectrum. Spectroscopy. This allows us, it allows the determination of the composition and conditions of an astronomical body. It's spectroscopy. In spectroscopy, we capture and analyze a spectrum. Spectroscopy assumes that every atom or molecule will have a unique spectral signature. And that's what I was saying, that each individual element, each individual atom of all the hydrogen atoms give off the same spectrum, but they do not give off the same spectrum as, say, an oxygen or a carbon atom. Each element has its own spectrum, and the study of that is called spectroscopy. So again, the study of the spectrum that these elements give off, these atoms give off, is known as spectroscopy. So the formation of a spectrum, two hydrogen atoms. For clarity, only the inner four orbits are shown. So there's only four of them shown. We know there's more than that. We talked about that already. But when it drops one energy level, say from 3, right here, from 3 to 2, in this hydrogen atom, an electron is dropping from orbit 3 to orbit 2. The emitted light is red. If the hydrogen atom, an electron is dropped from orbit 4 to orbit 2, the emitted light is blue. So this spectrum is going to be blue and red. All right. Key point, a transition in energy levels produces or absorbs a photon. So if it's dropping, it's going to produce a photon. If it moves out an energy level, it absorbs a photon. So this gives us three types of spectra or spectrums. A continuous spectrum. This is what comes from a black body, the sun, for example. Typical objects are solids and dense gases. Emission line spectrum. It's produced by very hot gases. Fluorescent tubes, auroras, and many interstellar clouds are typical examples. Then we have the dark line or absorption spectrum. Light from a black body passes through cooler gas, leaving dark absorption lines. Fraunhofer lines of sun are an example. So when I look at a hydrogen emission spectrum, I have these possibilities: 6 dropping orbit 6 to 2, 5 to 2, 4 to 2, and 3 to 2. When that electron drops on these levels, it gives off certain wavelengths of light. So if I was to look at nothing but hydrogen gas with a spectroscope, this is what I'm going to see. All right. Some of you have done that in my room before, where we looked at different lights with our little spectroscopes. If we looked at hydrogen, this is what we would see. All right. And on our lab, this is related right here. If I drop from 3 to 2, it's red. If I drop from 4 to 2, it gives off this bluish green color, and so on and so forth. This is what you should be drawing in your labs. So we looked at a hydrogen spectrum. Now let's look at the helium emission. Notice, and you know, just from looking at the periodic table, helium has 2 electrons. And because helium has 2 electrons, there's more combinations involved in gaining and losing energy. And because of this, helium has a different spectrum. Yes, these are the same. These are the same, but they should be because they have at least one electron. Now, there is green and there is yellow, and then there is another two separate colors that aren't in helium. If we put these two together, then now we know that the sun or a star has helium and hydrogen on it because when we look at them through a spectroscope, this is what we see. Now, when we look at that continuous and absorption spectrums, and we're just going to say, hey, here's a hot source, okay? And it's going to shoot out a continuous spectrum that can come down. We can shoot it through a little slit in the window. We can cover up the glass of a window, whatever, cover things up, shoot a light beam through this prism, and we get a continuous spectrum. Okay. The brightness, remember, I told you before, the higher the amplitude, the brighter it's going to be. And here's our wavelengths. It's going to increase as we go in this direction. If there is between that hot source a cloud of hydrogen gas, when we see the spectrum, these absorption, the hydrogen, let's go back up here. Remember, the hydrogen's going to absorb. It absorbs. So in this diagram here, as this hot body, as the light waves go through hydrogen gas cloud, it's going to lose this hydrogen gas cloud absorbs these wavelengths. Okay, it absorbs these wavelengths. That's what's causing this to get excited. It absorbs these wavelengths. So when I get the spectrum, those wavelengths will be missing. I can tell it's traveled through a hydrogen cloud. So an astronomical spectrum, we see here the spectrum of a comet and the sun. So we can see what the comet is made out of. It has some oxygen and hydrogen in it, some ammonia and different things in here because of the spectrum. When I look at it, only those colors show up, so I know what elements are in that comet. On the other hand, if I look at the sun, can I tell what's in the sun? Absolutely, I can tell what's in the sun. All right. There's some calcium missing. There's a little bit of hydrogen going here, some magnesium, and these are either absorption between us and the sun, or the sun lacks some of this. All right. The sun will lack some of these. And I can tell by looking at these spectrum. Gases in the Earth's atmosphere absorb electromagnetic radiation to the extent that most wavelengths from space do not reach the ground. That's why telescopes that are out in space, like the Hubble, the Chandra, and all these other telescopes, Kepler, it's important because they don't have these electromagnetic waves filtered out through the atmosphere. Visible light, most radio waves, and some infrared penetrate the atmosphere through an atmospheric window. Wavelength regions of high transparency. The lack of atmospheric windows at other wavelengths is the reason for astronomers placing telescopes in space. So let's take a look at these atmospheric windows. Here is my spectrum. This is what we can see. Notice the colors we see, they come through pretty easily. Ultraviolet, though, is really blocked out by the ozone. There is a small infrared window. There's other that can get in here too. Radio window, the radio waves. Radio waves are really important. Okay, we have a big window for that. But a lot of these other waves, water, carbon dioxide, they are completely blocked out, as are the X-rays, ultraviolet rays, and then the longer wavelengths like electric charges. Okay, they are completely blocked out. So it's important to have radio telescopes that see in ultraviolet and X-rays outside, like this right here. Okay. And these out here, we need these out here because we can't get a good look at astronomical bodies that are blocked. So much is blocked by our atmosphere. The Doppler shift in sound. Wavelength in sound is short and higher pitched. Remember, the tighter the wavelengths are, the closer they are together, the wavelengths, the higher the pitch. So, over here we're talking beep, where over here, longer wavelengths are slower pitch. So as it's moving towards you, like a snowplow piles snow in front of it, the sound waves are shorter. As it goes past you, they lengthen up. They start to drop away. That's why if you watch racing or you hear an ambulance or something coming towards you, it goes, the sound changes. It's lower pitched because the waves are spread farther apart. The Doppler shift in light. Longer wavelengths are red. The blue shift where it's jammed up. Okay. So with this in mind, if an object has a blue shift to it, we're going to think it's moving towards us, or the sound waves, like the snow, is piling up, or the light waves are piling up, where back here they're going to spread out. If a source of light is set in motion relative to an observer, its spectral lines shift to a new wavelength in a similar way. The shift in wavelength is given as a change in the wavelength, where lambda is the observed shift wavelength and lambda O is the emitted wavelength. V is the source non-relativistic radial velocity, and C is the speed of light right here. An observed increase in wavelength is called a red shift, and a decrease in observed wavelength is called a blue shift, regardless of whether or not waves are visible. Doppler shift is used to determine an object's velocity. An object's velocity in what direction it's moving away from us or towards us. All right. That is it for the notes on this chapter.